Hey everyone, Mr. Fugay here, and this video we're going to talk about 4 different applications of how we can use similar triangles to measure things in an indirect fashion. So, in other words, indirect measurement problems. So we're going to go through this where I'm going to show you 4 different problems. After each one, I'm going to try the A example, and then you're going to try the B example, pausing the video and giving it a shot yourself. So let's go ahead and get started. So in this first example, it talks about a flagpole casting a shadow, and a person nearby is also casting a shadow. Now, what do we need to do in this situation, and why is this true? Well, when we're doing this, if we take a look here, let me get my pen. You see we have our flagpole here, and then it's casting a shadow. And the person standing over here also casts a shadow. These are going to create 2 triangles, and they're actually going to be similar to one another. And the quick reason why that is because the person in the ground, the flag in the ground, are perpendicular. There's your 90 degrees. The sun creates the shadow, and the angle that the sun is hitting the object. So if the sun's up here, shining in this direction, it's going to shine at that exact same angle at the person here. And that's the reason why we can use similarity and proportions to help us find this height. So the flagpole's shadow is 28 feet long. Person is 5 feet 6 inches. Now we got to be very careful with this. This is not 5.6 feet. 6 inches is actually half a foot. So you have to take whatever this is and divide it by 12. So really this is 5.5. So let's go ahead and fill that in. And then their shadow is 3.5. So right away we can see our proportion. The height of the person is 5.5. The height of the flagpole corresponding is x. The shadow of the person is 3.5, and then the corresponding shadow of the flag is 28. So now we can use cross-multiplying proportions to help us figure out the exact height of this flagpole. So we're going to do 5.5 times 28. It's 154. We're going to divide by 3.5. And so this gives us 44 feet. Let's go ahead and add that unit on so that we know that that number actually means something. That is the height of our flagpole. Okay, so 2 separate things. Both are casting shadows, set up proportions, and solve. Let's go ahead and have you try example 1B. Go ahead and pause this video and give this a shot. All right, hopefully you've had a chance to try it. Here is example 1B. So we have a very similar situation, except this time it's a tree instead of a flagpole. So there are our triangles. Again, that third side is not directly really of any importance, but it does create those similar triangles. So once again, we're comparing the height of the person in the tree as one ratio, and the shadow of the person in the tree as my second one. When we cross multiply and solve, we would end up with a height of 27 feet for our tree. All right, let's try the second example. So in this second one, we want to indirectly measure the distance across a river. So what we're going to do is create some overlapping triangles to help us accomplish this. So you can see the different sight lines that were measured on the ground, and our goal ultimately is to figure out this length here, x. Now, what's important in this problem to notice is that we have 2 similar triangles. This time, they are inside of one another. We first have triangle PRE. That's going to be this green triangle right here. And I'm going to take that highlight and I'm going to drag it over here to the side. So x is the length of the river. 180 is that measurement that's made just on the banks of the river. And there's our first triangle. And for the second one, that's going to be triangle POC. So we draw that. We'll go ahead and take that and drag it over to the side. Now we gotta be careful about these measurements. The bottom is 350, but the length of this triangle all the way across is not 125 because that only goes from R to O. We would call this 125 plus X. Now quickly, why are these similar? They're similar because they both share a right angle here that was marked. And then this angle up top here, P, that is technically part of both triangles using angle as a reason why we're allowed to now set up a proportion to be able and solve this. So let's go ahead and do that. So we'll call it the height just because it's the vertical. The height of the green triangle, the height of the pink triangle is 125 plus x. Then the bottom side is going to be 180 of the green triangle, and the bottom of the pink triangle is going to be 350. Okay, setup is complete. Now all we have to do is go through the cross multiplying process. So this will just be a few things we got to throw into our calculators. The numbers might be decimals in these problems. They might be kind of larger values. We're trying to find real measurements of real things. And in fact, we'll be doing an activity eventually in class, whether we've already done it or we're going to do it, where we are actually going to measure some things ourselves using these similar triangle features. Okay, we're almost done the problem here. We're going to divide by 170. So 22,500 divided by 170 gives me value. Now this time I'm going to get a weird decimal. I got 132.2. We want to round our answer to the nearest foot. So we're going to go ahead and just say that the distance across the river is 132. All right, halfway through. Now it's time for you to try another one out. We want to find the distance across the pond here, just like the other problem you did. I want you to pause this video and give example 2B a try. Okay, let's see it. Here is the problem. Now, one thing I recommend, especially if you're doing this in OneNote, I think it's really powerful to be able to like trace the triangles out, drag them over so you can really get that perspective of what the measurements are here. So we have the bigger red triangle, which actually goes across the pond, and then that smaller green triangle that just goes right on the edge of the pond there. We can see the proportion is set up, cross multiplication, and we end up here. They wanted the nearest hundredth this time, so 183.75 meters. All right. This next example is going to be really important, whether we've already done it in class or we're going to do it later. We are actually going to do this in real time. You can use mirrors actually to create reflections as well to help us find the heights of various things. So in this problem, once again, we are 5 feet 6 inches tall. Just remember from the first example, that means that the person is 5.5 feet tall. A mirror is placed so that it is 11 feet from the traffic light. So the mirror is actually going to be right here, just so we're in reference here. 11 feet from the traffic light, so the mirror. And then it is 3 feet away from the person. So we have this here. Now again, why is this allowed to be proportion in similar triangles? Well, the triangles here are 90 degrees. The person and the traffic light are standing at a perpendicular. And a mirror, what it actually does is it uses a reflection. Well, a reflection means that the angle that the top of the traffic light is hitting that mirror is the exact same angle that the person's sight of line, so when they look down at the mirror, is actually going to see as well. Those are congruent angles. And so mirrors will actually create a reflection, which technically create similar triangles. And that's the reason why we're going to be able to find the height of this traffic light. So now it's time to set up the proportion. We have the height of the traffic light over the height of the person, and that's going to be equal to the distance from the traffic light to the mirror over the person and the traffic light. And just like everything else, the setup really is the most challenging part. Now we're going to go ahead and we're going to cross multiply and do the math to back our work up. Here we go, divide by 3. And so it doesn't give us a place to round here. I'm getting decimal of 20.16667. So let's go ahead and just call that maybe 20.2 feet. That's a good enough accurate measurement. That will be the height of the traffic light. All right, here's another one. No picture this time, but I want you to see if you can draw that situation and pause this video and give this one a try. All right, here is example 3B. So we have a flag that we were trying to use the mirror tool for. So we have measurements of 30 from the flag to the mirror. The person in the mirror is 4, and the height of the person is 1.6. Once you have the drawing properly made and labeled, the proportion now is just setting up those corresponding ratios. And there it is. We got an answer of 12 meters. All right, we have one last example we're going to do here, and you know what? Let's go ahead and do a little Phillies reference. If you're watching this in the spring, it's the beginning of the Philly season. Maybe in the fall, hopefully we're holding a World Series title. But regardless, the sun is going to shine down in Philadelphia today. The Fanatic wants to figure out the height of the bell at Citizens Bank Park. Now, the Fanatic is 6 feet tall. We'll come back to that in a minute. And casts a shadow 2.5 feet long. Now, here's what this problem is going to differ from all the other ones we've done. The Fanatic shadow is going to coincide with the end of the shadow cast by the bell. And then it was told that that particular distance, the Fanatic, is 21 feet from the bell. So we need to find the height of the bell. What is going on here with this whole coincide idea? Well, we have our Fanatic, which I'll draw in green. What's happening here is I'm going to move this triangle off to the side, okay? And actually, I'll get rid of that hypotenuse for now. So you have the Fanatic, and you have his shadow, all right? Great drawing. As he walks along, oh, maybe before we do this, I'll show you also the bell will create its own shadow as well. So it'll look something like that. So what happens is this right here is the tip of the shadow of the bell at Citizens Bank Park. The Fanatic is walking along, seeing his shadow, and as he walks into the shadow of the bell, the end of his shadow, the tip of his shadow, and the tip of the bell shadow will touch, will meet each other. And that right there is exactly what we need to try to create here. This is creating a situation of overlapping triangles. Now let's go ahead and fill in the given information and then set the problem up. So the Fanatic is 6 feet tall. His shadow is 2.5 feet long. Want to figure out the height of the bell. Now here's the key with the 21 feet. The 21 feet is not the bell's shadow. It is in fact the distance from the Fanatic to the bell, which tells me actually that the bell's shadow is 23.5 feet long. So if it's been helping to draw separate triangles, let's draw them out. We have x. Once again, that is 23.5. You would add both those numbers together to get the bell's shadow. Now the Philly Fanatic's a little bit easier to set up. His height is 6. His shadow is 2.5. So now it is time, just like all the other problems, to set that proportion up. Height of the bell, height of the Fanatic. Shadow of the bell, be very careful about that when these coincide problems, over the Fanatic's shadow. All right, 2.5x equals, let's get that calculator out, 23.5 times 6, 141. We're going to divide both sides by 2.5. And so the height of the bell at Citizens Bank Park is going to be 56.4 feet. All right, final time, I'm going to have you pause the video and try this last example about Lisa trying to find the height of a building. Go ahead and pause for this. And here is that last problem. So take a look here. Once again, we've got to be very careful that that 150 is not the shadow of the building. Rather, it is the distance from Lisa to the building. So we actually have to add Lisa's shadow onto that to get the 160.5. So that will conclude all of these problems here. However, I've got 1 minute left. I want to show you something on Delta Math real quick of a particular problem you might run into. So let's hop over there real quick. Problem that's going to show up in your Delta Math practice that doesn't really align with anything we just did in this lesson has to talk about a pole and a guy wire. A guy wire is something that supports a really tall structure. So this question is actually asking to find the length of the guy wire. So if you notice back on all the problems we did, we never really dealt with the hypotenuse of any of those triangles. We were always dealing with the legs essentially of that, the person in the shadow or the building in the shadow and so on. In this case, they're asking for the hypotenuse, which is the guy wire in this case. So if you look at this problem here, you will see they want to find this hypotenuse length. So how do you do something like that? Well, the easiest way I would recommend doing this is to find the height of the pole first. And then once you have that, use this big height, use this length, so 8 plus 3 is 11, and set up a Pythagorean theorem. A squared plus b squared equals c squared. And that's how you'll figure out this extra length. So do everything like you've done in the other problems, but remember to do the Pythagorean theorem at the end. Go ahead and try that out. And thanks for watching. Hope you have a great rest of your day.